Hello viewers, welcome to this lecture on the controllability of discrete time varying systems. So, let us consider the time varying system x of k plus 1 equal to a of k x of k plus b of k u of k as given in equation 1. So, the system is said to be controllable if for any initial integer k 0 and arbitrary vectors x 0 and x 1 in Rn, the state space, there exists an integer n, that is the final instant, and a control sequence u of k 0, u of k 0 plus 1 etc., u of k 0 plus n minus 1, such that the solution of 1 satisfies x of k 0 is the initial condition given x 0 and x of k 0 plus n is x 1, the final condition. So, if this is the case, then we say that the system is controllable in the time instances k 0, k 0 plus 1 up to k 0 plus n. So, now we will see that this controllability of the time invariant or time variant system, they are analogous to the continuous systems. So, in the previous lecture we have seen the Kalman condition for the controllability. So, similarly in this lecture we will see analogous result using the controllability Gramian matrix. So, before that let us write the solution of the equation 1 in the following way: x of k is phi of k k 0 x 0 plus summation I ranging from k 0 to k minus 1 phi of k comma I plus 1 into b of I u of I. So, we recall that the definition of the state transition matrix is phi of k comma any integer m, where k is strictly greater than m. If you have, then this is equal to a of k minus 1, a of k minus 2 up to a of m. So, this is the definition of the state transition matrix, and phi of m comma k, it means the inverse of this one, that is a inverse of m, a inverse of m plus 1 etc., a inverse k minus 1 is the notation for k phi of m comma k. So, using this state transition matrix and the properties, we write the solution of the system 1 as given in the equation 2, and then it can be using the property phi of k comma I plus 1 can be written as phi of k comma k 0 into phi of k 0 I plus 1. So, we can write equation 2 in the form of the next equation as given here. Now, because phi is invertible, we are assuming that all these matrices A of k are invertible. This inverse always exists for all k. So, with this assumption, we can take the inverse of the matrix phi k k 0, which is equal to phi of k 0 k. So, taking phi k k 0 to the left hand side, we get phi k 0 k into x of k, and taking this x 0 also to the left side, we get minus x 0 equal to this summation I is equal to k 0 to k minus 1, this expression. So, now we get the equation 3 by substituting the final time instant, that is when k is equal to k 0 plus n, which is denoted by k suffix n. We get from, in the place of k in the equation 2, we put k is equal to k suffix n here in this expression. We get this phi of k 0 k suffix n into x of k suffix n minus x 0 is given by the right hand side in 3. So, now we define the controllability Gramian matrix. So, if you recall for the continuous case we say W is equal to T0 to the initial time to final time of phi T0 S B of S B dashed of S phi dashed. So, this is the definition of the controllability Gramian matrix in the continuous case, where dash denote the transpose. So, the same similar definition replacing integral to summation and using the time instances like this. So, W is defined as summation I is equal to K0 and Kn minus 1 of phi of K0 I plus 1 B of I B transpose I phi transpose K0 I plus 1. So, this is the controllability Gramian matrix. So, the theorem analogous to the continuous case is the system 1 is controllable if and only if the controllability Gramian matrix W is non-singular. So, the proof is similar again to the continuous case. Earlier we defined the case. In the continuous case we define u of t to be equal to b dashed of t phi dashed T0 t multiplied by the Gramian matrix for continuous case, its inverse into phi of T0 and final time into x1 minus x0, the initial condition of the system. So, this is the one such control for the continuous case which steers the system is x dot equal to a of t x of t plus b of t u of t. For this we define the control. If we substitute this x of t0 is x0 and x of t is x1. So, u of t steers the system from x0 to x1. So, similar to this, for the discrete system we define the control given in the equation 5, which will steer the system from the initial condition x0 to final condition x1. So, this proof is direct, because if you substitute this control in the equation 5, in the equation 3, u of I we substitute as given in equation 5 here. So, if you see this, so if you substitute, this will be equal to summation I is equal to K0 Kn minus 1 phi K0 I plus 1 B of I. Now, in the place of u of I we substitute the definition b dashed of I phi dashed of K0 comma I plus 1 multiplied by W inverse into phi of K0 Kn into x1 minus x0 into this expression. Okay. So, if you substitute this, it can be easily seen that the bracket from here to this position, this indicates, or by the definition of W we can say that this is W and then W inverse, it becomes identity, and the remaining portion is phi of K0 Kn x1 minus x0, which is same as the left hand side. So, this implies that x at Kn, in that place you have x1. So, the final condition is given by x suffix 1. So, it means that the control given in equation 5, it steers the system from initial condition x0 to final condition x1. So, that is the proof for the sufficient condition. Sufficient condition means it is, the theorem is, if W is non-singular, then the system is controllable. If W is non-singular, we can use W inverse in this expression. So, by substituting this control, we get the controllability of the system. Similarly, the converse part, if the system is controllable, then W has to be non-singular. So, the proof is again similar to the continuous case, exactly same, wherever the integral is there, they are replaced by summation. So, that can be easily verified. So, it is necessary and sufficient that the controllability Gramian matrix is non-singular for the controllability. So, now we consider this following example, x1 of k plus 1 is minus x1 plus k times x2 of k, and x2 of k plus 1 is 2 x2 plus u of k. U of k is the control here. So, in this case the matrix A is time varying which is given by minus 1 k and 0 2, and the matrix B is given by 0 and 1, the control is u of k. Initial condition at time t equal to 0 is 4 and 3, this vector 4 3 is there, initial time is k0 is equal to 0. Now, if you see final, if you take final time to be k suffix n which is equal to 2, then we will try and the final condition is given by minus 3 comma 4 for example. So, we want to steer the system from the initial condition 4 comma 3 to minus 3 and 4. So, we want a control which will steer the system from this to this. There may be several control which will perform this solution, but we can find one such control here. So, this is the x1 axis and x2 axis, but we note that it may not be a continuous solution, it will be a discrete solution and it will find the solution in 2 steps, because at k naught equal to 0 the point is here, at kn equal to 2 it should be at the end position. So, in between you have only one point. So, we need one point as the solution, that is x at 1, this is x at 0 is the vector 4 3 and x at 2 is the vector minus 3 4, and we need this thing, and we also want to find the control u of 0 and u of 1, so that this control steers the system to this final position. So, if you directly apply the formula, the controllability Gramian is summation I ranges from 0 to kn minus 1. So, that is 2 minus 1, it starts from 0 and end with 1, phi of k0 I plus 1 b dashed phi dashed 0 I plus 1, that is k0 is 0. Now, we can calculate by recalling phi of km, it means a of k minus 1 up to a of m. So, when we take and similarly phi of m comma k, we have seen that it is a inverse of m etc. up to a inverse of k minus 1. So, this is phi of 0 comma 1 means it is a inverse of 0, and a of 0 is given here, a of 0 is minus 1 0 0 2. So, we can find the inverse of that, and a of 1 is minus 1 1 0 2. So, substituting those values, similarly phi of 0 comma 2 is a inverse 0 a inverse 1, that gives this one, and so for calculating W we need the summation of these two expressions, phi of 0 1 and b b dashed phi dashed 0 1 plus phi of 0 2 b b dashed phi dashed 0 2. So, summing this two we get the controllability Gramian matrix given by this expression, and can be easily verified that it is non-singular. So, according to the theorem the system is controllable. So, the control variable which we want to find is given by this expression. We have seen the formula in 5 is one control which will steer the system from initial x0 to the final condition x1. So, applying this formula we get the variables u of 0 is given by this expression and u of 1 is given by this. So, it will steer the system from initial condition 4 3 to final condition minus 3 4. So, this illustrate the way a method of finding a particular control for steering the system. So, with this I conclude this lecture. Thank you.